My take on that, like either the technology would advance, like you would have a better concepts of engines than what it is right now. Like rocket engines are not that good, you know, not reliable. And solar power doesn't cut it, you know. It's not enough to propel that power and push you forward. So there should be either you guys in the future, you're designing a new concept of engines. Engine doesn't mean gas-based, could be nuclear-based, could be...
Once we get the hydrogen, that might be the
Yeah,
fuel.
could be hydrogen, could
for
be
that.
anything else, you know. One time I saw a researcher who was working on ion-propelled devices. Like the ions being released from a chemical material, and believe it or not, those ions have weight, even though it's not considerable, but when they are released at a certain speed, then you can see that little tiny, very lightweight thing is moving. So that's the start point. Maybe in 50 years, 100 years, you will be propelled by ions, which is crazy. You know, you can imagine ions as marbles, like marbles are falling down and pushing stuff away. So we're still in our course, but today we'll talk about Introduction to Engineering Design. There's engineering and there's design. Objectives for this chapter would be you identify and explain the key steps in design process. That's one thing. Second thing, you need to explain what is the customer role in the design process? Where is the importance of customer in the design process? Why customer is there in design process? We thought design process is about engineering and engineers. Thirdly, we apply the design process so that we can solve open-ended problems. If you never heard that term, open-ended problem, mean a problem that doesn't finish. It's something going, development, and increasing the efficiency of the solution for your problem. Then understanding the importance of the engineering design process. Design process is an important thing. In the field, anything process related is a lengthy and could be bureaucratic for some people. It's not fast, but when you are working on complex problems, as we will see moving forward, it is important to have a certain process. Because when you're talking about design process, there is many people involved. Each person could be following the work of the previous one. There is no single person. It's rare to have somebody, an engineer, stay in the same company all his life. That's rare. The percentage is low. There is, but it's rare. So people need to come behind him and continue the work he's doing and continue the progress. Each person is putting his brick. At the end, you get a big building of a well-designed process. If I ask you, why are you planning to be an engineer? You would say probably, I need to design something. To design could be design, as you mentioned now, there's products 50 years from now. Those products, could be the next generation. You could be teaching the new generation to do those things. So you would say, I want to design water purifying system for off-road applications. Like let's say somebody is stuck in the middle of desert, he have water, maybe oasis or something, then he can't drink that water, but I can give him a purifying system on the go, solar-based, and he can be able to drink fresh water. Then you would say, some engineers would say, I want to design spacecraft that helps humans go to Mars. As Jordan mentioned, he got to go to Mars and starve there without water, nothing. Then a medical device that can help maybe heart stroke patients. You know, somebody when he have heart stroke, he didn't have enough time to reach the hospital in many cases. He's maybe in a remote area. How come if you have a kit that will help him on the spot? Then, engineers always thinking design a device, design a system, design a process. Not necessarily the engineer is designing. When you say design, I want to design a product, go SolidWorks, do something 3D for a device. It could be a process as well, like you are on a production line, or let's say you're thinking about the university system, how students get in, how they get out. Well, in the cafeteria would be more busy. Why would I wait in line? Why there's not more doors, or there's a way how people in and out so that it will always be flowing as it should be, or in the road system and so on. So engineer equals design. Engineers always design something. Now, what is engineering design in specific? We can define it as a systematic process where you use it to find solutions for humanity problems. Humanity obviously have a lot of problems, and this is a process. Problems of today are different than problems of yesterday probably, and they will be for sure different than the problems of tomorrow. So engineering design, you are in a systematic process to find solutions for humanity problems. I would add, it is a continuing solution where you always find developments and improvements for that problem. Now, if you say design with engineering, I say design is the base of engineering, as we mentioned. Then design process usually is applied for complex problems. Of course, somebody having a problem with his, let's say a company having a pen that will leak at the normal temperature, then he want to solve that problem. That's not complex, that's a simple problem. You can look into what kind of ink they use, they look at the whole design. But sometimes you have like a community problem or a society problem. It's engineering related. Let's say the water is polluted. What you're going to do about it, you need to go back and follow the design process to be able to tell how to solve that problem, as we're going to learn. So mechanical engineer designing an effective vehicle suspension system. That's a way of where design is in progress, and you need design process for that. Vehicle suspension system has been designed, as I mentioned before, by a team of engineers, not one person. This team could be changing. There is a process in place to make sure why our previous suspension, is this the first time we do suspension system? If it's not the first, what's wrong with the older one? Are the customers complaining about it? That's where customers come in the process. What kind of complaint they have? How are we going to make it better? Then are we designing the vehicle for the roads of Georgia, or is it for Michigan, or is it for another country, and so on. So that kind of things that you put in mind. Electrical engineer, you could be designing a portable wireless device that people are going to use for a certain purpose. Could be military purposes, could be civilian purposes, as we have our smartphones now. Material engineer could be designing a lightweight material composite for aircrafts, because aircrafts have a certain weight limitation. We're going to talk in the process as well about constraints. As you're thinking about design process, you're thinking about constraints as well. What are my limitations? Do I have like the sky's the limit in my design, or there's limitations? So that kind of design examples. Now, when you have a complex problem, we said there is a team on it, and this problem gonna take, solution could be obvious, but it's gonna take maybe years, maybe centuries to solve that problem, but they are progressing towards that. Same as what we see today as global warming. Assuming you agree with that, then there's a team, global team working on that and investigating and seeing what's the levels of water around the earth and what's going on. Is the temperatures being recorded higher than usual and so? So that would be a global effort, and there's governments involved in all of that. So it's going to take a while. Sometimes it's going to take, because of the process taking a while, sometimes because each individual need to have, or each team have a certain approval from a certain department to be able to move forward. So again, requires many engineers, disciplines. So you could be having mechanical, electrical, electronics, material sciences, and so on. Same as what NASA projects and National Science Foundation. They give researchers and professors around the world with their teams of researchers funding to do a little bit of research on a certain little thing in a big device, let's say that's going to go to Mars one day. So it's a group, it's a team. You have, of course, scientists, you have legal personnel, government, and so. Then you could apply a technology while considering public safety and awareness. As we mentioned about the water, when you want to change the water line, let's say in Georgia, instead of coming from Georgia itself, it's going to come from Florida, let's say. Then you're going to think, would the water pressure be less? Or does Florida have like a bad reputation about the water is not drinkable, or there's a problems could come in the way? Maybe everything is fine, but maybe problems show up in the way. Design process, let's mention again, it's not necessary you're designing a product. It applies perfectly for a product. You want to design a new wireless mouse, or you want to design a screen, that works. It could be a process, it could be anything else. So you define the problem to be solved. The second step, you collect the data about the problem and why it happened. So let's say a certain company, again, back to automotive, if a company keep having a flat tire on the highway for that specific trim of vehicle, let's say Ford Explorer, then why that is happening with that exact trim of vehicle? You want to know what's going on, collect data. Who are the customers who reported that? What area from the country the customers are reporting? On which road? Internal road or highway roads? That kind of thinking, like the wide, big picture thinking, that's the way you should think about the design process. Then you start to identify your solutions while keeping in mind constraints and criteria. Now, let's say back to the Ford Explorer, if the tire go bad on the highway, at what speed exactly does it go bad? 80 miles per hour, or is it the legal 70 miles per hour? Then let's go back. Are we providing those tires to the customers, or maybe the customers change the tires to another brand than the one we trust, or than the one that the factory recommend, and so on. So you look at constraints and criteria to be able to see your solution, how it's going to fall. Then you develop as well, you got your first solution, then you start to develop your alternative solutions. Like, okay, we can maybe go with a new tire supplier in the case of Ford Explorer. Or we can maybe limit the drivers or give them a hard note when they buy the vehicle, hey, this vehicle should not go ever above 75 miles per hour, otherwise you get a flat tire or exploded tire, and it's your responsibility. Then at the end, we have the initial solution, and we have the alternative solution. Now we want to select which solution should we go with after analyzing our alternatives. Now, should we change the tire supplier, or should we tell the driver not ever to go above 75 miles per
Change the
hour?
supplier.
Maybe, yeah. So at the end, you communicate and you document your results. Now, assuming that you went with that solution, or you had simulations on that solution that it's going to work or not, and of course you need to document that. As we mentioned, documentation it's reducing efficiency for engineers, and engineers hate documentation, including myself. But then as I'm growing older, and as I'm staying longer in the industry back in time, I realize how important is documentation, because when you are the one who's coming after somebody else, working on something important that could be life-changing for the company and for the customers, then you need documentation. Who did that? Why they did that? What kind of software they used? What kind of design process they went through? When you have the documentation, then you'll be a better engineer in delivering better product and solve the problem.
It's absolutely imperative from my experience.
Based on the vehicle that we mentioned, that the problem is you have a flat tire. We're going to have a problem though moving forward that you're going to walk you through your thoughtful process about it using the design process tips. But like you had a flat tire, or let's say exploded tire, which is more serious than a flat tire. On the highway, customers are complaining, tires are being exploded at a high speed. Now you have a steering wheel. In Florida, it's very hot for me. In Georgia, hot for me, I'm not used to it. Customers are complaining. That's where the problem always starts, by a product. Customer complaint, or usually the next manager would come into you, hey, we have a problem. How he know? Because customer complained. Customer complaint means less sales. That's where everybody have a problem in the company. So customers are complaining. That's the importance of customers in the process. They complain, and the steering wheel in summer is too hot to drive. Like now you leave the lecture to your vehicle, whatever vehicle we're talking about here, and just the steering wheel is almost melting, man. You need gloves to be able to drive. Otherwise, you need to turn on the AC and wait for 10 minutes, maybe open doors and windows. It's ridiculous. So people are complaining. They can't drive it comfortably. Let's assume the company care about the comfort of their customers. Many companies would ignore this complaint, but let's say Mercedes, they care about their customers. When somebody pay $100,000 for their car, of course they need to care about their wheels. Now, if you want to think using the design process about this problem, now we define the problem. What is the problem here?
Steering wheel's hot.
Steering wheel's hot. How about if the electronics are shorting out inside while you don't know? Does the car have a cooling steering wheel option? By the way, I never saw that anywhere. I don't know if it exists even. I know there's heated steering wheel. In Michigan they use a lot. So the problem is, the steering gets hot. If you want to get deeper into the problem, then what's going on is the heated steering wheel circuit shorting out. There's a lot of controls on the steering wheel. Maybe they're shorting out, that's one option. What kind of material are we using for the steering? You know, the higher brand cars, they put Alcantara on it, which is clothy. I hate it myself. It's like clothy thing. Some vehicles, let's say GMC in specific, Buick, which is like the luxury of GM or luxury, they put wood, still put wood on most parts of the steering wheel. Why would they do that? I think similar problems. So you need to know in details. Let's say here the problem is general. It's just too hot to hold it because of the weather. We define the problem, now collect the data. What kind of data would you collect in this case?
Temperature that it gets, where the heat's coming from.
Mm-hmm. So we'd study the location, we'd study how long he keep it under the sun, we study if the windows are being tinted or being heat treated and so on. How about the dashboard? How about the other components besides the steering wheel? Are they hot as well in the same temperature or no? Is the steering wheel failing or is it functioning just fine? We need to research that, collect more data on that. It's kind of adding to define the problem better, but then you need to collect data. What kind of material I'm using here? Exactly, if it's a composite, I need to know. If it's a plastic, I need to know. Then I would say how the vehicle geometry. Does it have a big window? Is the window like inclined with a higher degree, 45 and up, and so on. So that kind of thing, collect more data and try to see what's your solution is. Now, identify your solution constraints. So what's the limitation for your solution? Like you want to solve the problem that the steering is hot. Now you have limitations. First limitation, let's say the AC efficiency at the first minute of running the vehicle is too low. As long as the vehicle is not driving, as you know in your cars. You get AC, but not really a good AC, you know. So that's a limitation. I can't use AC to solve the problem. That's one thing. The other thing, maybe like the window is too big. Maybe the area is too hot. Constraints are out of your control. That's what we mean by constraints. Now, let's identify, after we identify the solution constraints, let's have alternative solution. So first we try to work with the geometry of the vehicle, make sure it maybe have tinted windows, and all of that details. Then now give me another solution than tinted windows. Instead of hot steering wheel, cold steering wheel? Maybe, like, is that easy? I know hot steering wheel, engineering-wise, you just put heating element, which is just a wire, basically. It's easy application. Can we do an application for cool steering wheel? Okay, let's say we had alternative. I have my solution. We'll have it in the next slide. What would be your conclusions? Like, let's say, okay, we tinted the windows, and now the temperature we used to estimate it to be, I don't know, 80 Fahrenheit. I don't know if that's even accurate. Then it went down to 75 Fahrenheit. Maybe 5 degrees are just fine. Let's look at the competitors. How hot are their steering wheels in a hot day and so on. So you get your conclusions, your documentations, and make sure everything is documented and the thought process being written down. My solution, just go to the nearest store and buy one of these. Maybe material would vary based on based on if the steering wheel material is attracting more hotness, then put one of these. It wouldn't be pure black, so that means it will not observe a lot of the heat. It will be a little bit less. Maybe the customer would not complain around that anymore. Again, that's not tested, nothing. I'm just assuming here, just for the sake of the argument. Now, let's define one more time the design process. Design process is 2 words. We have design and we have process. So design is a structured problem-solving activity, and process usually we identify it or we define it as a phenomenon that is identified through a step-by-step changes that lead to your required or needed results. Now let's go through details with the design process. We said first, we identify or we define the problem. Engineers, in many cases, they are not the one who define the problem as we mentioned, but the customers, and in many cases, company, field representatives, and management. Field representatives of company, usually they are in the market, they are in touch with the customers, and they hear from customers. So the problems for products coming from customers always. So the solution, in this case, if you want to try to add a solution at this point, it's premature and it's too early to add a solution before you know what's going on. So as an example, let's say a company needs to transfer their metal ingots from building A to building B. Now, if we want to define that problem, so we need to find a way to transfer the metal between building A to B. Then we collect the data. So the design team would be collecting the data and assemble all the needed information on the problem, and they use the internal company documents, in many cases available systems, internet search, and as well by asking the experts or the experienced engineers who know more than newer engineers in this case. Back to our example of transferring metal from building A to B. If you want to talk about data collection, you collect the data on firstly, how far is building A from building B? Then, is the metal would be transferred daily or just a one-time problem? Then what is the current transfer method, if there's any method that they're using right now? And what are the current load transfer methods available in the market? Like, can I buy something in the market for one time and use it to transfer that metal, and so on. Solution constraints. A constraint basically is a physical or a practical limitation on possible solutions, as we mentioned. Now for this case, solution constraints, building A and B are too close, there's a typo here, too close with little space in between for machinery, or you can say the building area is too busy and you can't apply any machinery or heavy machinery or cranes to do that. Then could be the metal ingots need to be transferred and stored at a certain temperature. That's a limitation. You need to be at a certain temperature, it will cost you more, you need a location, you need a certain treated storage and all of that. And could be building B having too many stories. Let's say it's a high building, then you want to go from story 1 to story 100, then that would be having a different technique to transfer the material in this case. Alternative solutions, then you have experience and knowledge to be able to provide alternative solutions. That's important. The team would usually get together so that they can do brainstorming, and the experienced one would get or give a better solution suggestions than the newer ones, and then the team together would analyze each solution and try to see which one they should go with. For the company material transfer, so solution 1 would be using a cart, alternative solution would be using elevator style lifter so that they lift the material, or could be using conveyor belt, or you can use those all together maybe to transfer the material to the new location. Your conclusions, usually the conclusion is the step where you spend most of your time in the design process, and you spend as well resources either on the design team or asking experts as an outsource to see what's their input on it, using, maybe you're paying for a certain company to give you certain data release so that you can look at it. Then those results will be communicated with all the details and reports needed for the design to be built and manufactured. Conclusions, solution 1, let's say, was interfering with constraint 1. Solution 2 is the best because of XYZ. When you have a design process, you need to have timing. Design process, we said it's a process, it is long, there's many details into it, there's many teams involved with it. So you need to have your timing in place so that you can, let's say, solve the problem at the deadline needed. So if the customer complains about certain thing, there is a deadline. You can't just keep solving that problem for 10 or 20 years. If it's an urgent problem, then you're gonna solve it in a reasonable amount of time, and it makes sense to keep always timing in mind. So as we mentioned before, complex problems need more preparation time. You need to keep your timing in mind. The bigger the problem, the more time it needs to complete each design step. Then design process have no end. So when you have your problem solved, problem is called open-ended, so always you have solutions and you have improvement to your previous solution so that you can always make sure your problem will not show up again in the future. For the people-related problems, then you need to be considerate about the safety of people and animal, and you need to have the right legal approvals. Timing chart, you need to always use a timing chart so that it's easier for you to evaluate the process timing and look at it through a chart so that you can avoid the interference between step 1, step 2, and step 3, and so on. So you can see here we have a timing chart in case you're wondering how it looked like. So let's say you have design steps here. I believe this is in your book. Activity time schedule, then the percentage of the total time. So let's say you identify the need, then you define the problem from here to here, then you start to search or collect data about the problems, let's say from here all the way to here. Then you go constraints, criteria, alternatives, and so on. And communication. Let's say here you have per month or per year, you have a certain deadline where you're gonna finish, and every time you are delayed at a certain point, you will be able to identify that right away, instead of realizing at the end that you've been 10 years solving the same problem. As well, we use other visualization to be able to look at the big blocks of the problem You could be having conceptual design, preliminary design, detailed design, prototyping, and final design, and design evaluation.